All right. So this week, this is our what is this, the fourth session that we've had or the third? Anyway, you should be finishing up chapter 5 and on to chapter 6. So chapter 5 of the system is all the different parts, the parts of the solar systems. One of the goals I have for that chapter is to get you familiar with the different pieces, why you would select one piece of equipment over a different piece of equipment. And then chapter 6, we jump into site evaluations, sort of what Brian was just talking about there, where I'm going to throw this to gallery just in case. There we are. And so the site evaluation to me is kind of it's a non-technical chapter in many regards, really just designed to say what are the issues that you're going to face when you go out there to do the site evaluation. So before I jump onto chapter 6, does anybody have any questions from chapter 5? Anything that you were coming through doing that you ran into? There were a couple of things brought to my attention this week that I fixed in case there were a couple of videos that were disconnected. I reference YouTube videos. So there were one about reading bidirectional meters. I've fixed that one, got a different video that I linked in. And then the one about the Ripper for shingles, using that tool. So there's a new one there. And I think maybe backing up a little bit, there were a couple of the labs. I fixed the PV Watts, or not the PV Watts, the NEC lab, the National Electrical Code lab, because the links there had come disconnected. I think we talked about that last week or the week before. So that should be all right now. And then the other one had to do with PV Watts references. The numbers in PV Watts had changed. So in one of the labs, the numbers were slightly different than what you got when you did the reading. So all of those are updated and fixed now within the system. In case you're one of those people who's behind, you won't even know what I'm talking about. So, Brian, you had a question?
Yeah, I had a couple. I put post-it notes in sometimes, and then I kind of figure it out later. But with DC conductors, it says it can be up to 1,000 volts DC inside the boundary of the array. But NEC says that what we have coming in the house can only be 600, right?
Let's see.
That's just a little confusing to me.
Yeah, that sounds confusing to me too. Where are you referencing that from?
Page 122.
122. Okay.
So, and it's like there's 3 bullet points there, and it's the third one down under the 2014 rules.
Yeah. Okay. Yeah. I think what that 1,000 volts DC in the 2024 rules, that was for commercial systems, so you could have up to 1,000 watts or 1,000 volts there. Now during rapid shutdown, it's got to be down to 80 volts. And that becomes important specifically when you're talking about putting together power optimizers normally, because the one of the advantages or one of the sales points of power optimizers is you don't necessarily have to have one optimizer for every one panel. With microinverters, typically you're going to have one microinverter, one panel. But you've got to have some sort of module level power electronic to shut off the panel at the site. So at the source up on the array. So let's say I've got 2 solar panels and I hook them together in a string and hook them into a single power optimizer, right? And from that point forward, the power is controlled by the optimizer. Well, that's acceptable, but what if the individual VOC of one of those panels is more than 40 volts, which on the larger panels, that can be a thing. Well, under that scenario, I couldn't hook two of them together within the array in a string because then my voltage is greater than 80. So I can't do that. I can only do 1-to-1 in those cases. So from a design standpoint, that's something to look out for. That 80-volt limitation was put in there when solar panels typically were like 32, 31 volts. So they were kind of going, you know what, two of them, that's fine. But more than that, we don't want to see. But now two of them might not be fine with some of the bigger panels. So you just have to be conscious of that. Any other questions from chapter 5? I know there's a lot of stuff there to absorb because this is all new information. Yeah,
I wrote this question down, and I'm not so sure why. I was on page 136 about the batteries and how they're rated. So a battery's supply is measured in energy, not power, correct?
correct.
Because it's measured in amps. So amps are the energy. If it was measured in power, it'd be watts, correct?
Well, watts is power, but a battery's energy is watt hours. And because you get amp hours, that's a measurement of stored capacity. So energy is just power over time. So watts times hours. So technically, we're measuring batteries in watt hours, not in watts, but we're measuring solar panels in watts. Solar panels don't store energy, so it's just instantaneous power. But with batteries, we're saying, okay, to really get what their energy capacity is, I got to multiply amp hours times watts, which will give me watt hours. So for example, if I were to short circuit a panel, touch the positive to the negative, nothing's going to happen because there's no stored energy. But if I were to do the same with a battery, the whole thing's going to go, it's going to fry the wire because there is stored energy within that battery.
Oh, okay.
Yeah. So
that's a good way to remember it then.
Yeah, because we've all shorted batteries at some point in some way. So yeah, it's power. And the idea of power versus energy is a little bit confusing. Because of course we talk about the power company too. You're buying power from the power company. Well, no, you're not. You're buying energy from the energy company. You're buying watt hours. You're not buying watts.
So power is watts and energy is watt hours.
Correct.
Okay.
And in fact, in most of the lithium ion batteries, they just simply refer to their capacity in terms of watt hours. They don't even tell you what the voltage is or what the amp hours are.
Well, I've been looking at the solar generators. I want to get one for my camper, and it's got a 30 amp plug on it. Yeah. But the solar panel or the solar generator is only like 2,400 watts. So I did the conversion, and you're only getting 20 amps, even though you got a 30 amp plug, unless you go with a higher solar generator like 3,600 then. Does that sound correct?
Yeah, even 20 amps sounds a lot coming out of one of those little solar generators. In class, when we do the hands-on labs, we're going to go ahead and put together solar generators, as one of the labs. And so I would suggest that you can build your own solar generator, and it's a nice project to do. And you can size it to whatever need you have for your system. So I've made solar generators that will run a 20 amp circuit, like a regular household 20 amp circuit, that will run chop saws, they'll run refrigerators, they'll run all of those kind of things. or we make one, you know, a small one that just runs a few things. Like we've got this little book. I'll give you a copy of it when we're but this little assembling a solar generator book.
Yeah, that'd be
So
great.
this gives you step by step how you size a solar generator, where you can buy the products, you know, and it's a fun little project.
I watched your video before I even started the course because
Okay.
the little toolbox with the 35 amp hour battery and the inverter and
Yeah.
stuff.
Yeah, you can build one of those for about $250. You know, most of the cost is in the battery and the solar panel.
Yeah.
So, you know, I figure $250 and you're paying $80 for the battery and $70 for the panel. So the rest of it's all about $100 for everything else you need.
Hmm.
So yeah, did you understand the difference there with amp hours in the batteries? The faster you discharge them, the less capacity there is within that battery. So that's kind of an important concept to understand, because I always think of it like if you drive a car, you know, if you're driving a car 35 miles an hour, you get a certain amount of miles per gallon. But if you drove at 200 miles an hour, it's the same car, but you get less miles per gallon because it consumes them at a different pace, at a different rate. So that's it. The faster you deploy the power within a battery, the less capacity it has to service that load. And in this chart that's on 136, it says that if you took it and deployed this one battery at 100 hours, so from full to empty over 100 hours, it has 2,490 amp hours. But if I do it all in 1 hour from full to empty, it only has 600 amp hours. So the rate of consumption affects the capacity of the battery. And that becomes important typically. Let's say that you've designed a system for a standalone home and you've sized the battery, you did everything, and you said, okay, this battery should be fine for you. And then the homeowner complains and says, you know what? I run out of power. The battery goes empty at 4 o'clock in the afternoon. You know, I don't have any power for the evening. And you're going, well, that doesn't make sense. I sized it all properly. And then it turns out they're running some big motor that just, you know, sucks the power out in a very rapid pace. So instead of having 2,400 amp hours, they've only got 600 amp hours just because they're stealing the power quickly. So that's the third part of it that we deal with. It's watts, watt hours, but then the rate of consumption is going to be watts per hour. You know, how many watts per hour are you using? And that's like miles per hour in that regard.
Yeah. If you like, we've taken a long trip out to Idaho, and if you drive a reasonable speed, you don't stop as soon. If we had a buddy bumped it up to 75 miles an hour, but it was taking more to keep you at that speed. And so then we just had to stop sooner. So it didn't really save us any time.
Right. Yep. So yeah, it's interesting. Everything is a balance. We're all in the world of Zen Solar. All right, I'm going to jump into chapter 7 or chapter 6. I mean, if there's no other questions on chapter 5, just do a quick run through. And I also wanted to remind, let's see, I don't think he's on the call. I wanted to just double check here in my emails because somebody had sent me a bunch of, Ted. So Ted, who's in the class, Yeah, not on the call. Ted sent me some pictures. So yeah, we're going to use his installation hopefully as an example next chapter when we get into design. If any of you guys have real world things you want to do as part of the design, you know, we can try and design a system for your home as a project. You know, just be ready. The main thing I'll need from you is a utility bill. So research your electric bill and we can size out a project. Just what, I mean, if we're going to practice doing projects, we may as well do real world ones instead of just make up numbers. All right, so the site survey thing, and I'm going to project, if you project yourself out that this is your business now you're in the world of installing solar, whether it's for your own home, but let's say that Mason has decided that the wonderful world of solar installation is where he wants to live, and he's going to go out there and make his living earning $42.50 an hour installing solar. And where that's actually, I've had some graduates, they just started up and that's what they started getting paid right off the bat is $42.50 an hour working on a utility scale system. All right, now you can start your own business and then you earn about $3.22 an hour, you know, if you're running your own company. But I always tell people that because I've been self-employed so long, they always say, so what's the worst part of being self-employed? And I always say, because I work for a jerk, you know, he's kind of a jerk. All right. So the first thing you want to know is how much sunlight is available. So a certain percentage of homes simply are not suitable for solar. Either the roof faces the wrong way, or there's lots of dormers, or maybe it has a slate roof and you don't want to disturb that. And there's no yard space for a ground mounted system, or there are too many trees or whatever, or there might be covenants in the homeowners association that are against it. So a certain portion are just simply not going to be suitable. Normally, the first step that you're going to do when you do a site assessment is do a remote site assessment. So in those cases, you're going to go and go into Google Earth, for example. So in fact, this is a good opportunity. I can, let's see, Brian, do you want us, were you willing to share like your home information so that we can, let's say we're going to do a site assessment for you. You just called up and said, I'm interested in solar. What's the deal? So what's your address?
It's Points, West Virginia, 25437. Do you want the street address too?
Yeah, points as in like I'm pointing.
Yeah, so that's the city, Points, West Virginia. It's
And
very small.
And your street address.
3110 Little Cacapon, Cacapon, Levels Road.
Levels Road. Okay. I suspect there aren't a lot of those named that.
It's an Indian name.
All right. So if I go into screen share, let's see if I can find, I'm going to share my screen here. Now you guys are going to see all these open. Let me see. So there's a program here that's quite nice called Open Solar. And somebody's trying to call. All right, so Open Solar is a nice free software for doing this kind of remote site and site assessments. So we can come in here and now it's asking me for your address. So I'm going to say 3110 Little Capon Levels Road, Points,
Yeah,
West.
you got it.
All right, so then it's going to pull up your house. So that looks like, does that look like your house?
Yeah, actually, it's my mom's house, but that's my address. We're right across the road, like up to like 10 o'clock or
Right up here?
yeah, going past that a little ways. So right there, the white one.
Okay. Right in there.
Yeah. And
All right.
Mason's in the one to the right, and I'm in the one to the far left.
The middle is our garage, which is actually where we would put the solar panels probably if we ever did do it for
Yeah.
our family.
The white roof here,
Yeah,
Yeah.
that's a garage.
that's the garage.
hmm
All right, so this is kind of what you do the very first time you go into this is we're saying, all right, here's your place. I can see that shading, if we go with the garage, and the garage would probably be my first recommendation as well, or a ground mounted system. That's always an option when you're in the country, but it's a little more expensive. So then we come in here and we say, all right, this looks like this is the spot. So we've done this assessment. Now on the north, which is up here to the left there, the top and left, because these always come oriented due north and due south. So the north, the trees aren't going to affect us at all because they're to the north of this array. If they had been to the south, then that might have been an issue. So this becomes our location. So then I'm gonna, let's say cancel. I haven't used this program in a while. Now okay, so if I say create a project, so I'm gonna try and create a project here. And it's got the address. I think that should have you already there. And I'm putting in all my sales, marketing and stuff, customer contacts, so on and so forth. At this point, it's going to want energy. So here you can add in, you'll get the electric bill and you can add in your exact consumption. We don't have that, but we would need it for your electric bill. And now I'm going to want to go ahead and draw my solar array.
You want me to get electric bill?
No, I don't want to go that deeply into this at the moment, largely because I'm still trying to remember design mode. I've got to move this image provider. We're using Google. There we go. Detect imagery. There we are. And I should be able, said add panels. Oh, yeah, and here we would sort of draw in the panels. But I'm not that keen on them being portrait because your trusses are probably going the other way. So going to get rid of these. And we've got to have some room there for the, so it looks like, yeah, now I can just move them around a little bit. So if we center them somewhere in there, I can probably zoom in a little bit just to make sure. That looks like that's about all that's going to fit on that portion of the roof there. So given that I've selected these Q powers and their 340 watt Q cells, now I could go in and select different panels and you can choose from any number of modules there. But this has just told me that with this, I've been able to put 18 panels on your roof, and it is 7.4 kW, kilowatt hours. And then it's going to ask me, okay, what kind of inverter do I want? And I can go ahead and select an inverter. I could use IQ7s here. In your case, let's say it's a 7 point something kW solar edge. So I should be able to just get by. I know they've got a 7.2. This is a 10. I'll just use a 10 kW. So I can kind of map out what I'm putting in a solar edge, isolate the strings, and so on and so forth. So here's where you would design your system. So when you get all the way through, I can start putting in incentives, I can put in batteries, I can put in all of these kind of things. And then I should be able to generate an online proposal where we come in and it already has some boilerplate stuff. Continue to the proposal, and then it generates a document that shows you a nice little picture of it here. And here's the product. And the reason why Solar Edge is free is they do product placement. You know, they do a lot of promotion of these things. So because I've selected a Solar Edge, now it's going to promote Solar Edge. Because I selected Q-Cell, it's going to promote that to the customer. And then there's some stuff here about how much you're offsetting. And it's a lot of little boilerplate stuff about how much you're saving. We didn't put any tax credits. It already put in the 30% tax credit right off the bat because that's universal. But there might have been some other tax credits that are available to you. But in this case, it's saying, all right, the system's going to cost $12,000. But because of the incentives, you're going to have to pay about $9,500. So it's used the preset amount of whatever per watt I plugged into this thing. So you can see pretty quickly, you can put together a proposal to take out there to a client or get a fair idea. This is showing that this system is going to pay for itself based on savings in about 10 years. So I could probably refine that down as I play with it. Industry averages right now are about 7 years. So
What's the name of that site? SOPEC?
oh no, SOPEC's a company I do assessments for. This is called Open Solar. And you can sign up for a free program, free subscription to this and just play around with it. It's one of the better ones that I've seen out there. A lot of these systems, they charge you, you know, gosh, $200 a month to be subscribing to these online evaluation systems. All right, so this would be part of the assessment where you're deciding, well, where did it get this data for your how much it's going to produce? Because this has already said this thing's going to produce 7,488 kilowatt hours per year. Well, in order to figure that out, it had to have some data. Now, I didn't really plug all of this in, but it did get the azimuth of the array. So I'm not quite sure. I think I got to jump into design. I think it's going to tell me what's the azimuth. Yeah, the azimuth here is 136. So 180 is due south. So because of the orientation of the building, this is kind of nice because we didn't have to go out there and measure, you know, and get my compass and figure it all out. We just used Google Earth and it already had an image and it's already knows what the orientation of that barn is. So we already know it's 136 and then it just estimated slope of 20. Now you might want to go out there and put a meter on that. You know, you can get an app for your phone and see what the slope is. But 20 is pretty normal there.
Looks like a 412 pitch, so.
Yeah, and I've got a table in here that I've calculated what 412 pitch is as far as slope. Yeah, 412 is 18.4 degrees. So 20 degrees, pretty good estimation. I could change this to 18 here, and it's not going to change the numbers that much. So now it's going to say 7442. I don't remember what it was before, but it wasn't too far different than that. Okay. So this is a tool. This is one of the tools you'd be doing. Another thing you'd be doing, let's say we said 136. I'm going to make a note of that. 136 and 18. So, and it's telling us based on this that it's 7442. Well, another thing we didn't factor in is how much, what is the D rate on that system? And somewhere within this program, if I walk through every step, it's going to ask me what the D rate is. But in this case, I'm going to go into PV watts.
What do you mean by D rate? I thought it was C rate.
No, C rate is for batteries. D rate is DERAT. It's basically saying it's not going to be 100% efficient. So how much inefficiency is in the system? And we have to derate it,
Oh, gotcha.
for inefficiencies.
Got it.
So what are the main inefficiencies that we're dealing with? Well, there's an inefficiency when you convert from DC to AC. So that's going to be within the inverter. Inverters usually going to add 2 or 3% now of inefficiency. Then you got voltage drop. Well, that's hopefully maximum 2%, but it might be more. So now we're up to say 5% inefficiencies. And then you can have aging of panels. Maybe we add another 2% and panel mismatch or connections. So in this case, let's just assume our system is going to be 90% efficient by the time we've added in all of the inefficiencies. And I like to be overly cautious with that. If I think that it's 92% efficient, I'm going to design it based on 90%. Because it's better to underpromise and overdeliver than overpromise and underdeliver. So in this case, I'm going to plug in your address into PV watts here. 310 little that's CAC.
PACA, yeah. There you go.
PAN levels.
PON.
Oh, PON.
Jay, can you hear me?
Yeah.
This is Josh.
Yeah.
I was wondering, so I'm a little bit ahead. In the D rate, it mentions in the online course, it mentions like obstruction or like debris, dust, stuff like that on the panels, and D rating for that.
Uh-huh.
Do you just automatically like make that 1% when you're coming up with your system, or do you do it based on where the system is? Like how do you incorporate that? Because
Yeah.
so variable.
Yeah, I usually, if I were in the desert, I would probably add a little bit more, but yeah, I usually just throw in like 3 or 4% miscellaneous stuff.
Okay.
That includes dust. In this area, the rain is supposed to wash off most of that.
Right.
Although pollen could be an issue, but if you wash it once a year, you're probably going to be all right.
Okay.
Then connections and the like. So yeah, you get into this kind of, eventually, if you do this, eventually you're going to come to a number that you like with certain product. So for instance, if you're doing microinverters, maybe you say, let's just always derate at 94%. Solar Edge, let's do 90%. And that seems to work out,
Gotcha.
based on these, unless there's something unusual.
Okay.
And okay, so here we've already decided in your system there, I think did it already close that? Let's see. Nope, there we are. Yeah, 6.120. So the system is 6.1. So you've got a 6.1 kW system. System losses, this is where we're putting in the D rate. So I'm putting in a 10% D rate. We've said that the angle here is 18%. And we said that this one was 136. And so now we put in our numbers. Now I should see how much this thing actually produces. And here it's saying that our daily insulation is 4.27. And for that size array, it should produce 7,471 kilowatt hours per year. So let's see how close This one said 7,442. That's pretty close. So within 30 kilowatt hours per year. So obviously they're using numbers that are pretty similar, 10% D rate, more or less on that. They pull the numbers from PV watts, so it should be close if you're using the same inputs. So this is telling me this is how much it's going to produce. Now, in this case, Brian, if this was for your system, we would look at your electric bill, and this is going to generate about 7,500 kilowatt hours per year. The average home uses in America about 900 a month. So you're going to have about 10,800. Is that right? Over the year. So 3/4, little less, 70% of your annual from that array. So if you wanted it bigger, if you wanted more, well, you'd probably have to find a different location. Or put panels in this design. We could, in fact, put some panels on the north side here. It's not going to be near as efficient.
What
But-
about a standalone panels like between the two, like going towards our house in the center, but doing it on the ground to the
Yeah.
to the left, the other way?
Oh, over here?
Yeah, right. We're seeing like right there. Yeah.
Yeah, we could. Now, I wouldn't do both because I would just go, you know what? Now you're doing two systems. It's going to add to the cost. But if you wanted to get to 100% and you want to do a standalone unit, well, yes, for sure. You could do a standalone, and we could sit here and we could put in a second or our primary one, which in this case, I want to add some panels here. Let's say that we decide we're going to build a little solar carport, and I like, why not orient it due south? And Iron Ridge has a unit that'll take 5 panels, like that. So right there, we're making, in this case, this one is, well, let's get rid of this solar array. Are you sure you want to get rid of it? Yep. All right. So now it's telling me I've got 25 panels and it's going to generate 10,500. So right there is, if you're doing 900 a month, that's exactly what you need. So a little array like this, you could just make a solar carport, and pull in your vehicles or whatever, park in the shade,
I like
store.
that idea because you're getting more bang for your buck. If you're going to do a standalone, then you also to have a carport or a shelter of some sort.
Sure.
You're splitting the cost then. Of the
Yeah.
structure.
Yeah. In fact, let's see, I don't think I was going to just say I could take the camera and just point it out the window over here. We've got a solar carport out behind the building here, and that's where we park. And it's quite convenient. It's nice. It looks nice. And we've got a car charging station right next to it, for the electric vehicle and all of that. So it's great.
Jay, in the winter, those trees to the south, do you think those would shade the array?
No.
No?
And I know that you could say, all right, yeah, that might be a problem. I just know that they're far enough away just from experience that they're not going to impact.
And they're downhill quite a bit also.
Okay.
So, yeah. But you could take a solar pathfinder out there and do a measurement, and that's what you would do on a site assessment for sure.
Okay,
Is
right.
you would go in there and set that up, but it's not going to impact. Plus, also remember in the wintertime, these trees, the deciduous trees are going to lose their leaves.
Oh,
So,
right.
even in that case, it's often minimal. It still has an impact, but it's minimal.
Okay.
If I were dealing with a place that had shading issues on part of the array, I would definitely go with Enphase microinverters, because then the panels that are not shaded are not affected.
Okay.
where a string inverter, even a Solar Edge one, is going to be affected somewhat. So in this case, because we can, one of the nice things about solar array is that you can orient it, a ground mounted one, you can orient it ideally. Where if we put it on the roof, we had to go with the orientation of the building. But a ground mounted system, I can come in and, like we did here, just simply oriented due south. No problem. So ground mounted, if you have the space, is kind of nice. And you don't have to worry about roof issues. You don't have to worry about removing it if the roof has to be repaired or something like that, or putting holes in the roof. It's a standalone thing. Also, if you're in a city, you may not be required to have structural permits because you're not really impacting the structure of the building. You're building your own structure. And the city is usually going to be less concerned about it because they're like, okay, well, if your solar array falls over, well, it falls over. I don't care, but if a building falls over, well, then there's possibility of loss of life or injury or whatever. So they're much more concerned about habitable structures. Was it clear to everybody about declination? The fact that south is not south, north is not north. It always reminds me this, we always used to tell kids when they came to Blue Rock Station on school tours, I'd always say, come here, kids. Here's the thing. Everything you've ever learned in school is wrong. And they'd always go, yeah, I knew it, and it's like, okay, well, now south is not south. Well, what do you mean? Yeah, so magnetic south and solar south are completely different things. So at the Mississippi River, they pretty much line up, but magnetic north is measuring a field of magnetism within the Earth's surface, and that's moving. That little magnetic center is moving. It's currently off the coast of Alaska, and it's moving in a direction. It's under the Earth's surface, shifting. So it varies. It varies quite a lot if you're up in Maine or Washington by as much as 18 degrees. Here in West Virginia, it's going to be around 8 degrees. So if you face something using a compass and you face it south, you're actually facing it 8 degrees off south. Actually it's orienting to the east of south. So just be aware of that. It's better if you're using a compass on your phone. Sometimes they have little, you can say, do I want this on magnetic or true south for the compass? Because if it's using GPS, it's going to be true. It's going to be true orientation.
So to find true south, then we just have to move 8 degrees to the west then.
Well, no, if you're in the east of the Mississippi, you're going to adjust your compass 8 degrees to the east. If you're it's west, it gets confusing because in the book and everything's always oriented based on north, and we're worried about south. So it's west for north, but it's east for south. Or just use your phone. That's easier. The concept of winter bias and summer bias, everybody clear about that? Here we're dealing with, I'm going to stop the share there. So here we're dealing with the fact that the sun is higher off the horizon in the summer than in the wintertime. It's lower on the horizon. The other issue there to consider, and most of the solar arrays that we're going to be dealing with summer bias because the days are longer in the summer. So you get more of your sunlight in the summertime, and the sun is clearer. I mean, there's less cloud in the summertime than there is in the winter, just seasonally in this part of the world. So if everything were even, if every day was the same length and the weather was the same year day in and day out, we would base the angle on latitude, because that's where you are on the equinoxes, on the spring and the autumnal equinox. That's when you're at a 90-degree variation. I'll try and see where the camera is. Yeah, so if this little thing here, yeah, you can't get there. I'll use my mouse pad. Whoops, I just lost you. I grabbed the mouse pad and it messed up my, so I don't see where you are. There you are. Really. All right, so if this is the solar panel here, right? Then I want, if this is the, if the panel is angled at, I get something flexible here, on the equinox. So this would be based on latitude. So if I'm at 40 degrees north latitude, the angle would be 40 degrees. And on March 21st and October or September 21st, we would have a 90-degree between the panel and the sun. But in the winter, the sun would be more down here. In the summer, the sun would be more up here. And the angles would not be at a pure 90 degrees. Because the days are longer and the like, we want to flatten the panel a little bit so that it's a summer bias. And we do that 15 degrees. So summer bias is latitude minus 15 degrees. And that just takes into account the fact days are longer in the summer and there's more sunlight in the summer. Winter bias would be latitude plus 15 degrees. Well, why would I use a winter bias? Couple of reasons. One is if I'm at a high north latitude, I might want the snow to slide off a lot easier. So I might want my angles to be steeper so that I don't get snow accumulation. But more often, if you're doing a standalone system, you don't really care about annualized production. You don't care about maximizing the annualized production. You care about getting power when you need the power, because you don't have a utility that's storing up a credit or anything like that. So what you do is you take the worst month as far as production versus matching it with consumption. So you say, all right, what if I use proportionally, let's say in December, I generate 70% of the energy I generate in March. If I use 70% of the power, no problem. I'm cool, because I'll just keep it oriented that way. But what about if in December I use the same amount, let's say I use the same amount of power every month, it's consistent, which is rare. Then what I would do is look at the month that I produce the least amount of power and size my system based on that month. So that in the worst case scenario, I still have enough power to power all my loads. Okay, have I lost anybody there? It's like, let's say December is the month that I produce the least amount of sunlight, I produce the least amount of power, but my load is consistently 500 kilowatt hours a month in, month out. Well, then I need to design my system so that in December, it produces 500 kilowatts of power. Now, in July, it might produce 800 kilowatts of power, but I'm only using 500. I don't care, because that's wasted power. Okay, fine. But if I produced it based on the averages, I'd still produce too much in July, but I wouldn't have enough in December. So I want to make sure it's producing everything I need when I need it. So that's when you might use a winter bias. And that's pretty typical. And there's a formula, I think I've got it in the book here somewhere, where you can figure that out. It's called the critical month design ratio, I think is the term there. And you just basically say, how much am I producing each month? How much am I using each month? Divide one into the other, and the worst month is the month we're going to design it to. That's kind of it.
So
But that's usually, yeah, go ahead.
Is that more important for the standalone systems as
Yeah.
opposed to? That's what I thought.
Yeah, it's only really critical for standalone, because with grid tied systems, you've got the grid there. So if I underproduce, I can pull from the grid. And typically the grid is going to store up credits. So kind of what I'm looking to do with the grid tied system is maximize my total year production. So there I'm looking at averages. Because I may produce too much one month, not enough another month, but at the end of the year, everything balances out. Although utilities are changing the way they're billing stuff. And so they're paying you wholesale for your power and they're charging you retail. So you may start getting into some of this design month stuff, because if I'm selling power to the utility at 5 cents a kilowatt hour and I'm buying it at 20 cents a kilowatt hour, well, that's not an even share.
Mhm.
So I might want to design it to produce when I need it so that I'm not getting ripped off that way, similar to a standalone system. But with a system like that, typically you're going to just simply add batteries, and that's going to be a cheaper system than increasing the size of your array based on the worst month. So everything always comes down to what is the most economic option, because you have a million choices. And oftentimes students will say, can I do this? And can I do that? And we're like, yeah, of course you can. Can you do it affordably? Well, that's the issue, because, you can do anything if you've got enough money. We see that in some of our politicians, right? So
even though it might be tempting to gear it towards maximizing the power in the summer by doing summer buys, if you're grid tied, you might want to make it work best in the winter so that you won't have to buy the power when it's more expensive.
yeah,
So
that may
you're
very
saying-
well be the option, because if I'm paying 4 times as much for the power I buy from them as I'm being paid for when I send it back, I might find that it's better to just invest a little bit more and produce more in those months that I need it. It may
Okay.
turn out to be the best economic choice.
Jay, do you
So-
think as utilities, change the way they're billing, it sounds like it would become more important to start incorporating like articulating arrays into the
Oh.
build.
Yeah, that's a good question. You're talking about tracking,
Yeah.
like, yeah. Yes and no. I think it's probably better to design a stationary array for a homeowner that's bigger, as
Mhm.
opposed to doing a tracking system. Because one of the big advantages of solar is there's very little maintenance. But as
Right.
soon as you start putting something that's moving, now you got maintenance.
Right. Yeah.
And it's going to break down. So, anything that moves ends up breaking. So I would just go with a bigger system if
Gotcha.
you want more generation.
That makes sense.
So how
Uh,
does the adjustable frame the mounting systems, how does that work as far as the the person who owns the solar panels, how do they adjust that themselves?
Well, there are several different types that are out there. Of course, there's single axis and there's dual axis. So let's just assume we're talking about single axis, where you're either adjusting the angle or the orientation, the azimuth. Most of the adjustable ones deal with the angle. And if it's a manually adjustable one, it can be just as simple as, for small systems, there are 3 holes in the back of the frame, and you go out and pop the screws out of one and then just push the whole thing up and then stick it back in there. And that's, the adjustment from summer to winter bias. And that's a good option for very small systems. And that's not something that's going to break because you're doing it manually. And I've seen some systems like that. But if there are 10 panels, say, on that system, 10 panels is a lot to try and move. So you've got to get 3 or 4 guys out there and you do it all and you push and then you stick the bolts in. And that all works, but not for a roof mounted system, because a roof mounted system, you want it to follow the angle of the roof. You don't want to adjust off of that. So these tracking systems are only for ground mounted things. A secondary option is one that's going to move automatically. That could be motor driven. That's very common, but that uses power and it tends to break. There are also ones that are hydraulic and thermal driven. So they use water difference in pressure. So the sunlight will heat up one side of the liquid and it'll expand and cause the array to shift. So it's using that. It's kind of a passive motion thing. Those are a bit expensive and complicated, But they certainly work. And then of course you got dual axis. Those are typically top of pole mounted systems where they're shifting not only angle but azimuth, so they track the sun throughout the day. Those are the most expensive. Those work well too, but usually are only viable if space is very, very limited. So for instance, let's say that you're putting in a system in a townhouse in a city, and the homeowner only has 20-foot wide backyard that goes maybe 20 feet deep. So that's the only space they've got, is a little, so you can put a little pole mounted thing that'll track the sun, because they may not even own the roof. Maybe it's a shared unit, so they couldn't put it on the roof. They've got a tiny little backyard. That may be your only option. But once again, the ones I've seen of those, they always are stuck in the position that they were in when the motor broke, and then nobody's bothered fixing it. So that's kind of, and so that's not ideal.
And does that come back on the installer in the end when the motors start
No,
to
I mean, they
fail?
typically have warranties. So let's say that a panel has a warranty of 25 or 30 years, but the motor only maybe 6 months or a year.
Hmm.
And and then of course on the 366th day it breaks if it's got a 1-year warranty. And at that point, yeah, they'll call the installer, and the installer may say, yeah, I can come out and fix it, and I'll charge you $150 an hour or whatever. So I just shy away from that. I mean, if space is not an issue, I just go with a fixed system. It's
That's
just a
kind of
lot.
what I was thinking about. If you start installing a lot of those ones that are adjustable or they are sun tracking, eventually you'd start just getting a flow of phone calls, probably like, hey,
Yeah.
my panels aren't adjusting. Can you come out and fix it?
Yeah.
That's just kind of what I was picturing.
Yep. And
End
of
up with
course,
a negative Yelp review.
yeah. And of course it's your fault because,
Uh-huh.
yeah. Well, the other thing is the other tracking system, and I'll sort of close with this because we're at the end of the hour, is let's assume, trying to get some props here. Let's say that this is the arm, this pen thing is the arm of the solar array, and this is a panel. The utility scale ones typically do an east-west tracking. So this rocker arm is gonna, like in the morning, if this is facing east, and then as the day goes on, it's noon and it's facing straight up. And then as the night goes on, it goes like that. So the whole array, this is going north, south, and then the panels are facing east and west. So they rock like that. Well, that's how utilities are typically doing it often. And the reason is they have people who work on them for maintenance. So they've got employees there, so it's not a big deal. But there are a couple of real advantages for that with big systems. One is you're going to maximize production during the day. You're going to be facing the sun all the time. But let's say there's an extreme weather event that comes up, like heavy winds, for example. Well, you can just lay the panels flat and the winds are just going to sail right over it and cause less damage. Or let's say hail is going to come forward. Well, you can orient the panels straight up and down. So now the hail comes down and it doesn't damage the panels. So you can react to weather events using your, remote control of these tracking systems. So if you're ever driving down the road in the middle of the day and you see a solar field and all the panels are sticking straight up, you probably know that a hailstorm is coming, and that they've put them in a preventative. So you take your car and put it in a garage somewhere, or drive under a bridge, get that thing protected. All right. Okay. I think now's a good time to stop on that. Next week, we're going to jump into chapter 7. That's when everything sort of comes together. We start doing design problems. And that's when the fun begins. I think that's when you guys start getting confused. So
I thought I
make
was
sure,
already.
yeah. Well, make sure you write down your questions. And again, throughout the week, if you get it frustrated, if you get to a place where you're feeling frustrated, just drop me an email. I'll respond to your specific question. No reason to wait until next Tuesday. We'll try and get that taken care of. Because I don't want you to be sitting there frustrated for 3 or 4 days waiting for the class time to ask your question.
And so you said Ted sent you his system. I was thinking of far as what I'm thinking about for my camper. Can I send you that kind of stuff and we
Sure,
could
sure,
decide?
yeah.
Okay.
And I just say also, and this is something I've been getting a lot with when people put files on like Google Drive or something, and then they share it with me. Give me permission to actually look at the files because I'm all the time getting these things. Could you look at this file? And then I go to open it, and it's like, oh, now I got to request permission to look at it. It's like, I anticipate I'm going to look at it. So give me permission. All right. Okay. Well, we'll see you guys next week, and I'll encourage you to join in Solar Noon Tuesday, of course, which is an hour before this one begins every noon. You should be getting those notices. If you're not, check your spam and make sure that, you can join in if you're wanting to do a total geek out on solar for every Tuesday. So, all right. Take care.
All right. Thank you.
Thanks.